In this session, I'm going to prove three things. The first thing is this, is that if y is equal to e to the power of x, then dy dx is also equal to e to the power of x. Number two, I want to prove that if y is equal to log x, where ln here is the natural log, meaning the log with a base that is equal to e. So this is really equal to log with a base of e times x. I want to prove that y equals to log x. If y equals to log x, then dy dx is equal to 1 over x. And number three, I want to prove that if y equals to x to the power r, okay, where r is any number, meaning it doesn't have to be a whole number. It can be any fractions, for example. If y equals to x to the power of r, then dy dx is the familiar r x to the power of r minus 1. So this is the formula for differentiating powers of x, and we'll show how we can actually prove this quite easily once we can do 1 and 2. Let's start from 1. So y equals to e to the power of x. The way I'll do it is to make use of the series expansion for e to the power of x. That's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... So to differentiate I can do it term by term. Differentiating 1, I will get 0. Differentiate x, I'll get 1 plus differentiate x squared. Okay, I'll get 2x over 2 factorial, differentiate x cubed, 3x squared over 3 factorial. Now let me just add one more term to make it more obvious. The next term here should be 4 factorial plus ... So differentiating x fourth, I would get x cubed 4 over 4 factorial plus ... Okay. Now you might wonder that if I've not proven this, if I've not proven this formula, how can I use this formula here when I differentiate the powers of x? Well, I can't unless I can prove that this formula is true when r is a whole number, unless I can prove this using a different method, just for the case when r is a whole number. And this I shall do in a separate session. But for now, let's make this quite clear, that when I do this differentiation, I'm using the formula that dx to the power of n over dx is equal to n times x to the power of n minus 1, where n is an integer. Alright, so I need to make use of this formula. Whereas in this case, I want to prove this when the power is any number. For example, right, let's make this quite specific. I'll just say when r is a fraction. So as to make this clear that I'm trying to prove something that is different from this formula. So this formula would be a result that I shall prove in a separate session, but I'll make use of this now. Okay. Right, let's continue with this dy by dx. We can simplify this. 2 factorial is just 2, so 2 and 2 cancels, I get x there. Now 3 factorial is really 3 times 2 times 1, so 3 and 3 cancels, and that leaves 2 times 1 at the bottom, which is 2 factorial. Similarly, 4 factorial is 4 times 3 times 2 times 1, and 4 on top cancels with the 4 here and leaves 3 factorial at the bottom. There. If we now compare this with e to the power of x, you see that the first 4 terms are exactly the same. And no doubt if we carry on writing for the next term and the next term and so on, they would all look the same as, or in fact they would all be the same as the terms in e to the power of x. So this means that this result is actually equal to e to the power of x. And that is exactly what I want to show. That if y is equal to e to the power of x, then dy dx is e to the power of x. So here I have proven this first result. Let's continue with number 2. In number 2, I want to show that if when I differentiate log x, the answer is 1 over x. So I shall start with y equals to log x. Okay, let me make that more explicit. I'll call it log to base e of x. And this means that x is equal to e to the power of y. Right, so let me now differentiate this. on both sides. I shall differentiate with respect to y. Okay, I shall making use of the previous results. Alright, I know that when I differentiate e to the power of x, like this, I'll get back the same e to the power of x. Right, this is when I differentiate with respect to x. Now I have e to the power of y instead, down here. But let me differentiate with respect to y on both sides. So d by dy of e to the power of y is equal to dx by dy. Okay. So from the previous result, I know that this should be still e to the power of y, and that's dx by dy. I can invert both sides to get dy over dx on the right, and here I get 1 over e to the power of y. But we know that e to the power of y is x. So therefore this is equal to 1 over x. And so I've proven the results. Let's go back and check. Right, the question is to show that when I differentiate log x, I get 1 over x. And here I've shown that the answer is indeed 1 over x. So this completes the proof for this part. So this proof makes use of the result from the first formula. Moving on, I now want to prove the third item. For fractional power of x, when I differentiate x to the power of r, I get this. Y equals to x to the power of r. Now in the first step, I would take log on both sides. So log y is equal to log x to the power of r. Log x to the power of r, we can bring down the power like that and becomes r times log x. Next, I shall differentiate both sides by x. I need to make use of something called the chain rule. So this is something that I shall prove in a separate session as well. But for now, let's make use of the result. The chain rule says that if I have a function y equals to a composite function, let's say f of g of x, then when I differentiate this, okay, let me change this notation. It might get a bit confusing. Let me say that I have z is equal to that z is a function of y, and y is in turn a function of x. Let me write it this way. So according to the chain rule, if I want to differentiate z with respect to x, I must first differentiate z with respect to y, and then multiply this by the result for differentiating y with respect to x. So first I differentiate with respect to the first function, the function in, which is the variable of z, and then I have to differentiate y with respect to its own variable. So that's the chain rule. And to apply it to here, I would have to differentiate log y. Okay, but I know that y is a function of x. So then I must multiply this by differentiating y by x. So I've just applied the chain rule. So that this is like the z here. Okay, so the function here is log of y, and y itself is in turn a function of x given by that. Then next, I have to differentiate the right side by x, and we already know how to differentiate log x from the last step. It is 1 over x. Okay, let's press on. D of log y by dy. Okay, it's the same as differentiating log x by x. So instead I've changed the variable to y. The result is the same, like what I've done here for the x. I'll have 1 over y for this times dy by dx. And that's r over x. And now I can make dy dx the subject. Alright, this is what I want. I want to find dy dx for this formula. I can multiply both sides by y, so y comes over to the right, r over x times y. Okay, and since y is x to the power of r, this would be r over x times x to the power of r. And x to the power of r divided by x is x to the power of r minus 1. And this is what I wanted to prove. If you look back at the question, I want to show that when we differentiate x to the power of r, we'll get x we'll get r times x to the power of r minus 1, which is what I just got. Okay, so stop here.